Okay, but actually, what is this? Hello, welcome to the Genuine Approachable Sudoku for the 16th of February, 2024. It is Lines Crossed by Philip Newman, featuring this insane-looking grid of lines. So, what are the rules? Normal Sudoku rules apply, so place the digits 1 to 9 every row, every column, and every 3x3 box. Entropic lines, along orange lines, which are the vertical ones here. Each set of 3 cells must contain 1 high digit, 1 medium digit, and 1 low digit. So for example, these 3 cells, those 3 cells, they must contain 1 medium, 1 high, 1 low. So if that cell was, for example, a high digit, and that cell was a low digit, then that cell must be a medium digit, which could be a 4, 5, or 6. Next, along teal lines, which are the horizontal ones, each set of 3 cells must contain 1 digit, 1 from 0 mod 3, 1 from 1 mod 3, and 1 from 2 mod 3. Now what is modular numbers? Each number, when you divide by 3, gives you a different remainder. So for example, if you divide 5 by 3, you get 1 set of 3 plus a remainder of 2. Therefore, it is of 2 mod 3. The 4 is of 1 mod 3. The 6 is of 0 mod 3. And from the digits 1 to 9, you can get 3 digits that are of 0 mod 3, 2 digits that are of 2 mod, 3 digits that are of 2 mod 3, and 3 digits that are of 1 mod 3. And so, for each teal line, any 3 sets of lines, or any 3 adjacent cells, must contain 1 from each type of mod 3. So for example, if that cell was a 2 mod 3, then because there's a 3 mod 3 here, there's a 0 mod 3 here, and a 2 mod 3 here, this must be 1 mod 3, which would be a 1 or a 7. So yeah, those are all the rules. With that, let us see if we can solve this entire set of puzzles. Well, we might as well start with we have a lot to go with, right? Because all these digits do give us stuff. This 3, for example, on the modular line, well, okay, I guess first, because we're doing this from like the beginner's point of view, let's try and prove how the line works. Why is it that the line must always be a sequence of 3 different mods? Well, whatever this mod is, that is 0 mod 3, so let's mark that. Those 2 digits will be of 2 different mods, which I'll mark with a different color, because there cannot be any repeated mods in 3 of these cells. Therefore, what color is that cell? That has to be orange, because it can't be pink or green. And so you can continue that logic and say that is also of that mod. And then after doing this, you can basically do the same with the other colors as well. And even if you don't know their mods, you can definitely say it goes in this order like this. And the same can be said about the vertical lines, which is why I can then prove that along each line, for every 3rd cell, they have to have the same mod horizontally, or the same entropy. I don't know. They have to be of the same level, I guess, vertically. So let's start with the 3 here. Those 2 digits are also 0 mod 3, and therefore have to be 6 and 9. We can probably do that with like a lot of the rest of these horizontal lines. Like this one here means those cells have to be 4 and 7. 2 here means those cells have to be 5 and 8. 4 here means those cells have to be 1 and 7. 5 here means those cells have to be 2 and 8. And we can probably do that for basically everything. Those cells are 3 and 9. Those cells are 1 and 4. 8 here means those cells are 2 and 5. 9 here means those cells are 3 and 6. And then we can probably go vertically and now say this 9 means that those digits are of the same level because it's an entropy line, and so must be 7 and 8. And I don't know if I want to fill up all the columns first before I start making those deductions, like this must be a 1. But I think we'll do that. The 3 here means those digits have to be 1 and 2. The 8 here means those digits have to be 7 and 9. 4 means those digits have to be 5 and 6. 5 means those digits have to be 4 and 6. 6 means those digits have to be 4 and 5. 2 means, oh, those digits have to be 1 and 3. 7 means those digits have to be 8 and 9. And the 1 means those digits have to be 2 and 3. There you go. That is everything we can uncover so far. So let's start doing actual Sudoku. For example, 7-8 pair removes 8 from that cell, removes 8 from that cell, removes 7 from that cell. And then we can do a bunch of other deductions based on that singular deduction alone. 8 means that's 7, 7 means that's 9, therefore that's 3. And then this even spreads over to here, so that's 7, which doesn't do anything, but 8 here means that's 2, 3, 2, 5, 3 means this is 9, so that's 8, 3 means that's 1, therefore that's 3, this can't be 3, so that's 6, this means that's 2 because of the 5 here, 6 means that's 3, 4 means that's 1, we have a 4, 5, 6 chocolate teapot here. What else can we do? 8 means that's 9, therefore that is 6, therefore that is 9. 9 means what? I don't know. 9 here though means that's 7, so that's 4, so that's 7. This can't be 5, so that's 8. And there you go, that's all we can do right now. We have a lot more chocolate teapots, but let's keep going with those digits, which have to be 1, 2, and 3. 1 can't be there, 2 can't be there, 3 can't be there. Those are 7, 8, and 9. 7 can't be there, 8 can't be there, 9 can't be there. I could probably do... no, we can't. Wow. It's all ordered in such a way that no matter which you pick, it's always going to work. No, this 2. That has to be 2 mod 3. There you go. So if those two are 2 mod 3, this cannot be a 9 because that's 0 mod 3, so that's 8. Which means that's 7, so that's 9. And now... yeah, because of this being 1 mod 3, this can also be 1 mod 3, so it has to be 2 mod 3, that's 5. That's 6, that's 4. The 6 here should resolve this entire set. 4, 6. And then we could probably do something with those cells there. Yeah, yes, that is 2 mod 3, so that can't also be 2 mod 3. That must be just 3. 1, 2. 3 means that is going to be 0 mod 3, which has to be 6. So those digits are now 2 and 8, which we can place because there's a 2 here. We can probably do regular Sudoku at this point, which I will do. That has to be a 9, I believe. Those digits are 3 and 4. Yep. Those digits are 5 and 7. Yep. Those digits are 6 and 8. Yes, we can do that by this 6 over here. 1s can't be in those cells, so 1 goes there. The remaining digits are 4 and 9. Yep, this 9 resolves that. Those digits are 4 and 5. 4 here resolves that. Those digits are 1 and 8. The 1 means that's an 8. Well, that digit is just, what, a 7? So those digits are 3 and 4. 3, 4. Those digits are 2 and 9, which we can place. Those digits are 5 and 6. Those digits are 2 and 5, I think. So that's 5, that's 2 because of this 5 here. The last 3 digits are 3, 6, and 7. 3 can't be in those cells, so 3 goes there. This can't be 7, so that's 6, that's 7. Solving the puzzle in 6 minutes and 48 seconds. Wow, that's quite cool. We didn't actually have to use the modular lines too much. I think this might have been more of a showcase that such a grid was even possible, because I am very surprised that such a grid is possible. I assume the digits here mean that there can be, you know, multiple solutions to just a pure orange and teal grid. I wonder how few numbers you actually need though to prove what the grid is. Right. Yeah, you don't really... I don't think you need that much. I don't think you need all 9 digits. In fact, if you remove the 5 in the middle, you could probably solve the puzzle as well, but that's just a very small step. Huh. Okay, well, that's very interesting. Hope you enjoyed this puzzle. I definitely did. Yeah, I'll see you next time. Bye bye.